Okay, so hi and welcome everybody in this edition of the Motivic Geometry Seminar. We're very pleased to have Baptiste Calmes report on new exciting developments in Hermitian K-theory. Please.
Well, thank you very much for the invitation. It's a real pleasure to speak at this seminar in such a beautiful room with nice paintings on the wall and to breathe electronically the fresh air from Oslo. So I will give an overview of a new definition of Hermitian K-theory in some sense. And I will explain one of the applications of that new definition, which is a proof of some conjectures of periodicity of Max Karoubi and Giffen. So this is joint work with a long list of people. The reason is that we started working on this project separately and then noticed that we were all working on the same thing, and we decided to join forces and to do something together. So my co-authors are Emanuele Dotto, Jonathan Harpaz, Fabian Hebestreit, Marcus Lan, Kristen Moy, Dennis Nardin, Thomas Nikolaus, and Wolfgang Steimle. They're spread all over the planet somehow, mostly in Europe. Okay, so the general plan for the lecture is to start by saying a few things about K-theory, classical K-theory. Of course, everybody attending the seminar will probably know everything that I say, but I'm just saying it so that you understand from which perspective we are approaching this subject. Then I will say some things about Hermitian K-theory, mostly in sort of the classical version of Hermitian K-theory, and I will state the conjectures in that language. And then in the sort of second part of the talk, I will explain this new approach. So I'll give this new definition of Hermitian K-theory quickly in some sense. And I'll try to give a sketch of proof of how this Karoubi-Giffen conjecture is proven. And then if time permits, I'll describe a few other features of the formalism and what you can do with it. Right. So let me start with classical K-theory. So I'll start with the K-theory of a ring, just to give a general idea. And say you want to define the K-theory of a ring, the first thing you start to define is K0 of the ring. And so what do? You take isomorphism classes of finitely generated projective modules, left modules if your ring is not commutative, you fix that. And you take the direct sum to turn it into a monoid, a commutative monoid. And then you take the associated group, you group complete this monoid. And that gives you K0 of the ring. Now, more generally, if you had some category that is additive, let's say it has a direct sum, and on top of that, you have some kind of notion of exact sequence in that category. Well, I do not want to give details on what that should be in every case, but you can guess. Then you define K0 as isometry classes in C with the direct sum again as addition. And you'd kill exact sequences. So when you have such a sequence, you could say that you have this equality in K0. Right. So in some sense, K0 has a universal property. And what is that universal property? If you state it simply, it says that if you have a function from objects of your category to a group, that is additive in the sense that anytime you have such an exact sequence, then your function satisfies this equality. Then, of course, you can factor the map that you have from the objects of C to G through K0. And of course, this map is a natural map from the objects of C to K0, sending an object to its isomorphism class. So I'm just noticing that I did not say that in some sense, of course, your exact sequences need to be compatible with your direct sum, but that is understood. Now, say you wanted to define, higher K groups. Basically, what is done in every setting, and there's been lots of setting in history for defining these higher K groups. It more or less can always be understood one way or another. And of course, you have to work through technical details to see it that way, but that is sort of what's going on. It's that what you kind of do is you take some category which has the features above, and you, in some sense, group complete it, but at a categorical level. And then you realize you take some geometric realization of your category, and you take the homotopy groups to get the high K groups. So that's been, in most cases, the approach. And I know Dan is in the room, so of course, he can interject and say that you can not do that, but still. Anyway, so for projective modules, if you were to take projective modules on a ring as your category, which is the sort of most basic thing you would like to do, then the first thing you would take is you take only isomorphism classes. So you take the groupoid core somehow of that category. And it's a symmetric monodal groupoid with a direct sum. And you do some kind of group completion. So you have a construction that does group completion. And then again, you realize that as you take the classifying space and you get a K-theory space, which is a group-like infinity space in the sense that it's homotopy groups. I mean, pi 0 is already not just a monoid, but a group. And of course, the higher ones are your other higher K-theory groups. So that, in some sense, is the general classical approach to K-theory. And now, it's hard to actually, in this language, give a universal property for K-theory, higher K-theory, or for that space, if you want. But more recently, with the development of maybe something I should say before that is that words on group completion. How should group completion be understood at that categorical level? Well, you can understand it that way. You can look at symmetric monodal groupoids, and you can look at the ones that are group-like. So being group-like is just that if you have a symmetric monodal groupoid, then it's the pi 0 of its realization is an abelian monoid. And of course, among those, you have some of them for which the pi 0 happens to be not just a monoid, but a group. So elements have inverses. And group completion is in the joints, the left adjoints to the inclusion here. Right. So
sorry, Baptiste, and such an adjunction always exists.
I'm sorry, I didn't hear you properly.
Such an adjunction must always exist.
Oh, well, it depends on your context somehow, but let's assume that it does. This is just a general introduction. I don't want to go into details here. I just want to sort of focus on the kind of approach we're taking. But in the setting that I will explain, yes, we will have this adjunction precisely. Okay, so several authors have proposed a sort of more modern definition of K-theory. So I do not claim to have a complete list because I'm not completely sure, but certainly there's some work of Barwick, of Blomberg, Gepner, Tabuada, and of Gebner-Mandel on the subject. For example, the paper of Barwick is extremely clear. And it uses the language of infinity categories. And somehow the definition of K-theory becomes that it's the universal additive functor from some stable infinity categories, so some type of infinity categories in which you have the usual categories of interest, to spectra. So the fact that it maps to spectra and not to spaces makes it automatically group-like somehow. But if you were to map to spaces, then you'd need to actually add this in, not just in parentheses. And it's the universal such thing that receives a map from the group width core. So again, as we had a map from objects in K0, that's what it is. So of course, this is not really a definition in the sense that you need to work to prove that such a universal thing exists. But nevertheless, it's extremely beautiful that we now have a sort of universal approach to K-theory. And in some sense, this talk is about the same type of approach, but for Hermitian K-theory. So I did not say what additive really means, and I'll say it now. So additive actually means that it sends certain types of sequences that are actually both fiber sequence and co-fiber sequences in that world to fiber sequences in spectra. So you get long exact sequences in homotopy groups, etc. So these fiber co-fiber sequences I'll call Vertica sequences. And of course, it's part of the beauty of infinity categories that you can actually make sense of fiber co-fiber sequences in this infinity category of categories. So actually, if you really want to know how this is defined, it's defined as some kind of loop spaces of a span category, which is a little bit like a higher, a higher span category, which is a little bit like a Q construction. Right. So now I'll explain certain things about Hermitian K-theory and try to follow the same approach. So again, I'll start with a ring. This time I'll ask this ring to be commutative. This is not a restriction that we put in the paper, but or in the series of papers, but I'll just use that restriction here to simplify a bunch of things. So first of all, I'll introduce very classical objects. So a quadratic module, which is a pair MQ, is a finitely generated projective R module in this talk, and a quadratic form. So I'll just recall very quickly that quadratic forms means that, of course, it is quadratic in the following sense. If you multiply by an element of the ring inside, then you pull out a square outside. And also it means that if you take the difference between Q of X plus Y and Q of X and Q of Y, then this actually defines a bilinear form that is, of course, automatically symmetric. Right. So it's also useful to have some kind of non-degeneracy condition. And you say that the form is non-degenerate, the quadratic form, if this associated pairing is perfect. And so it induces a perfect duality between M and its dual. Now, let me give you an example of a quadratic space. If you take any projective module, a finitely generated projective module, you can construct the so-called hyperbolic space. So it doesn't sit on L, it sits on L plus its dual. And the quadratic form that you put on that space is the so-called hyperbolic form. And it's just the evaluation. If you take some guy here and some guy here, you can just evaluate that one on here. That is a quadratic form. And of course, it's a very basic one, and it's we're going to use it all the time. And so it's called a hyperbolic module, and it is non-degenerate in the above sense. Now, we need some kind of slightly more refined notion of hyperbolicity in some sense, and you have things called metabolic spaces. So some guy like this is metabolic if you can do the following thing. You can find some other projective module L inside M such that, first of all, the quadratic form restricts to L as the zero form. And also, if you take that exact sequence, well, of course, you have this isomorphism from. Oh, sorry. Yeah, I should say that I'm asking that Q is non-degenerate in that setting. So you have this isomorphism between M and its dual, and so you put these two little exact sequences together, and of course you get a map here between the kernels, and you're asking that this map be an isomorphism, and so is that one. So when you can do that, you say that your space is metabolic. So when you can find such an L. So it's easy to see that the previous the hyperbolic space is metabolic, with L being L. And now you can define the Grothendieck fit group of your ring. So again, you take isometry classes of non-degenerate quadratic modules. You put the direct sum or the orthogonal sum, and you get a monoid. And you kill certain elements, and what we actually kill is you identify metabolic spaces and hyperbolic ones. So in some sense, sort of force these type of sequences to be split. So this is called Grothendieck fits group, the 0, 1, and I'll put a little Q because we're using quadratic forms, and that will sometimes change in the talk. So that again is a very classical definition, and sometimes I'll replace a quadratic by other types of forms, and maybe the ones that I also use the most often are bilinear symmetric forms. So of course, you know that in characteristic not 2, if you're over a field, say, of characteristic not 2, then quadratic forms are the same as symmetric bilinear form in an obvious way, but it's not true in general, and our formalism does not want to assume anything about characteristic. Right, so I'll now try to explain what these conjectures of periodicity are. So for that, let's introduce this groupoid, of finitely generated projective or modules, again with the direct sum that we used to define K-theory. And we'll introduce similar monoids. So quadratic forms, again, you take the groupoid, you just keep only isomorphisms, non-degenerate ones, and you take again the orthogonal sum, or symmetric non-degenerate bilinear forms. And some last thing that you actually need is so-called even forms. So it's again the same type of monoid, but you're asking that your symmetric bilinear form actually comes from a quadratic form. So it's in some sense it sits in there, but it's only the ones that are the polar form of a quadratic form. So these are called even forms because if you look at what they are over Z, you'll find that the number 2 comes up. Right. So we have all these groupoids, symmetric monodal groupoids. And then you can find the following spaces. The K-theory space, which again is group completion by classical techniques. So again, think of the plus construction, etc. So it's some classical group completion of that thing. And then you realize it to spaces. So it's a space. You have the quadratic Grothendieck space, which is doing exactly the same thing, but with this second groupoid. And similarly, you have the symmetric Grothendieck space and the even Grothendieck space. So you have these spaces and their homotopy groups. And now there are 2 interesting maps that relate K-theory to Grothendieck theory. And it's first of all the hyperbolic map, which sends a projective module to the associated hyperbolic module that I explained above. So this exists in all sorts of flavors. So I'll use a star instead of either quadratic, symmetric, or even. It's not a grading, it's just a star, a beautiful star, not a grading star. And the other way around, you also have another map. And it's just the forgetful map. If you have a quadratic module, you can just keep the module. So that way you have a map from K-theory to Grothendieck theory with whatever flavor, and also from Grothendieck theory to K-theory. Right. Now, you can look at fibers of these maps, and they're called the U and the V spaces. And by fiber, I mean homotopy fiber. Now, what do these conjectures of Karoubi and Giffen say? They say that if you take U of quadratic forms over R, and there's a little sign here that because you ask that the bilinear form is anti-symmetric and not symmetric. Well, it says that you get a space that is homotopy equivalent to V even. And if you take loose space over U of, again, anti-symmetric even quadratic forms, then you get V of symmetric forms. So there was a bunch of evidence, of course, for these conjectures historically. And they emerged more and more precisely across the years from the invention of Hermitian K-theory by Karoubi, Villamayor, and until more recent years. But let's say this is a fairly recent version of the conjecture. There are more general versions involving form parameters and so on. We also proved these versions, but I will not explain this during this talk for simplicity. So these are the conjectures. Now I'll switch to our actual approach to Hermitian K-theory. And for that, I will start by explaining what we define Hermitian K-theory of. So we will define Hermitian K-theory of so-called Poincare infinity categories. And these are actually stable infinity categories together with a quadratic functor. So I'll say a few words about stable infinity categories and then on quadratic functors, and then put these together. So I will not say what an infinity category is. I'll consider this reasonably standard by now. If you do not know what it is, you have to think of a category as having objects and morphisms, and infinity categories have higher morphisms, so they have one morphisms, two morphisms, three morphisms, etc. Not just one morphisms as usual categories. And basically, what is extremely interesting is that all the notions of category theory have been developed and formalized at the infinity level, so they're extremely pleasant to use these days. Especially, so there are different flavors of infinity categories, different versions that are in some sense all equivalent. We work with the ones mainly developed by Joyal and Lurie, called quasi-categories, but our proofs will work with any other model. So among infinity categories, you have some categories that are stable. So it's a property of infinity categories. It's not extra structure. And what does stable mean? So first of all, it means that you have a final and initial object at 0. So they're pointed if you want. It also means that every morphism has a fiber and a cofiber. Once you have 0, you can make sense of what a fiber is and a cofiber. And it also says that if you have a null sequence, so a sequence like this that sort of factors through the 0 object, it is a fiber sequence if and only if it is a cofiber sequence. So this is the fiber of the next map, if and only if this is the cofiber of that map. Now, this implies lots of interesting properties. So we'll call the suspension fiber of that map, and the loop the cofiber of that map. That's essentially unique maps in both cases because it's the 0 object. And the fact that the category is stable tells you that, or you can take this as a definition. And, I mean, there are various equivalent definitions, but let's say that you have the fact that these suspension and loop or inverse equivalences. So now that we have the definition of a stable infinity category, let's just see a few stable infinity categories and understand what features they have. So first of all, it implies that they have all finite limits and finite colimits. That's formal. It also implies formally that the homotopy category, in which in some sense you identify morphisms up to higher ones, is naturally a triangulated category. And for those who like triangulated categories, the fiber cofiber sequences in the stable infinity categories are the ones that give rise to triangles. So in some sense, you can consider them as an enrichment of triangulated categories. So the nice thing now is that they're much more flexible. You can do lots of construction to build stable infinity categories that you cannot do with triangulated categories. So I will not really use triangulated categories in that talk, but let's say that for all the people who've been working with triangulated categories, this is the way to go from stable infinity categories to triangulated ones. Right, so let's give a few examples just to fix ideas. So if you take a ring, again, you can take complexes over that ring, and you can take various derived categories of complexes. And they have infinity structures. So in this, the usual derived category in the classical sense is somehow a triangulated category. So it's just the usual category, but you can naturally define triangulated category, infinity categories in this realm of derived categories, and their homotopy category will give the usual derived category with its triangulated structure, and we'll use perfect complexes. So over a ring, it's just bounded complexes of finitely generated projective modules, and if you were to work over a scheme or something like that, it's locally that way. That's one stable infinity category that we will use all over the place. And there's another source of stable infinity categories coming from topology, and in some sense it's a universal one, in a sense that I don't want to explain right now, but it's an extremely important category for that reason, and it's the infinity category of spectra. So I assume in the seminar that most people know what spectra are, but if not, just think of indexed families of spaces. They're a way of stabilizing topological spaces. And formally what they are is you have indexed families of spaces, and you have maps from xi to the loose space of xi plus 1 when x is such a family. And of course, they should satisfy a bunch of properties, but essentially these maps will explain how things are stabilized. And they have homotopy groups, etc. Stable homotopy groups. So there's a relationship, of course, between spectra and spaces. There are functors, joint functors. First of all, you can take the suspension spectrum of a space. So if you have a space, you can take a space, its suspension, etc. And that will give you a spectrum with obvious maps. And the other way around, if you have a spectrum, you can take the first space. Of course, the spectrum should be properly represented in some sense, an omega spectrum, and then you have a space. So I'm saying this because we will define things that go to spectra, but they give you spaces just by taking omega infinity, and yeah. So there's another reason why spectra are extremely interesting and fundamental here. It's because naturally every stable infinity category is enriched in spectra with the tensor product of spectra, which means that there is a natural way each time you have two objects in a stable infinity category to get a mapping spectrum. So a spectrum of maps from X to Y. And we will use this. Right. Now, last notion that I will use all the time is that if you have a functor between stable infinity categories, and again, I'm not really saying what it means, but it means something on both on objects, morphisms, and then on higher ones. And it is exact if it preserves finite limits and colimits, if you have stable categories. And these functors will form the one morphisms in the infinity category of stable infinity categories. Let's now explain things about quadratic functors. So quadratic functors were defined a long time ago by MacLean in a certain context. And they were revived somehow by Lurie to study L theory. And they're extremely convenient for our purposes. So I'll say a few words on quadratic functors. So they're in some sense an abstraction of the following situation. if you take projective modules, you can take all the quadratic forms that live on that projective module. All quadratic forms, not just the non-degenerate ones, all of them. For example, you have the zero form. That gives you an abelian group. You can just sum quadratic forms by their values. And if you try to study what properties this functor has, well, the first thing you want to know is somehow, is this functor linear? In the sense that if you take a direct sum, how is the quadratic forms on a direct sum related to quadratic forms on summands? And the answer is that it's easy to see that there's a piece that is the summands, but there's a remaining piece. So if you want the actual maps, they go that way. And take a quadratic form and you restrict it to one summand, to the other summand. And you can also you can get a bilinear form from one summand to, the product of the summands to R by just taking this kind of polar construction on the quadratic form. And that is an isomorphism. So what it says is that if you're looking at the functor that takes a module to the quadratic forms that live on that module, well, it's not linear, but the difference to linearity is some kind of bilinear thing. So MacLane formalized all this, and we'll use a sort of modern version of the formalism in terms of quadratic functors to spectra. So instead of abelian groups, we'll take spectra, and we'll start with stable infinity categories. And so you need a bunch of conditions for this functor to be quadratic. I'll just state these conditions, but they're sort of what you need to express what is above. So first of all, you want your functor to be reduced, and then you want it to be too excisive. And this means in practice, so too excisive it comes from Goodwillie calculus. But if you don't want to go into that concretely, it means that first of all, so your quadratic functor is reduced, it sends 0 to 0. Then naturally you can, by functoriality, you can split off these summands, and the remaining thing has to be exact in both variables. So this is a spectrum. Huh? And then there's one thing that does not appear in the above example that needs to be taken into account, is that there's a natural map from your quadratic functor applied to an object in your stable infinity category to this polar part somehow. And this polar part, of course, if you apply it to one space, there's a C2 action on that. And this map actually lands in C2 fixed points, homotopy fixed points. And you can take the fiber of that map in spectra. And you want this to be exact in X. So that's what a quadratic functor is, but really you should think, in some sense, as a first approximation of that, you should think of that idea. So there's an equivalent condition on a cofiber, but we don't really need that, but it's symmetric in some sense. Okay. Now, what will we use them for? Well, we'll think of, when we have a quadratic functor, we'll think of this as the spectrum of some types of forms, like, for example, quadratic forms on the object X. And we'll think of its associated space as the space of quadratic forms or some type of forms on X. Of course, when I say some types, it's because we can define all sorts of quadratic functors, and some of them will be related to quadratic forms, some of them will be related to symmetric bilinear forms, etc. Now, let's look at a bunch of concrete examples. So again, let's use this derived category, so infinity derived category. you can do the following. You can take an object M, so a perfect complex, and send it to the mapping spectrum from M tensor M. So this, of course, means derived tensor products because we're working in this infinity category. You can map to R, and again, there's a C2 action because you can permute these factors, and you can look at C2 orbits. So that's one thing you can do. The other thing you can do is you can actually take C2 fixed points. Then if you do that, you can easily see that if you just plug in some actual module and you put it in degree 0 in a complex, you'll actually recover quadratic forms on M. And there you recover symmetric bilinear forms on M. Of course, seen as an abelian group inside spectra by Eilenberg McLean.
Sorry, quadratic forms here, you mean a non-degenerate quadratic?
No, I don't mean non-degenerate.
Arbitrary.
I mean arbitrary.
I see, okay.
Again, this is an abelian group. So you see if you cannot sum on the same space non-degenerate quadratic forms, right? They won't stay non-degenerate. When we sum, we're really summing the values. We're not doing orthogonal sum. We're not, the space doesn't change. I mean, the underlying module doesn't change, right? You have to think of this as the set of quadratic forms on a given module. For example, you have the 0 form, right?
Yeah.
Okay, good. Right, so if you take homotopy groups, you exactly get that. Right, so there's a more subtle family of examples, and it's constructed that way. Now, if you take projective modules, you can include them in their perfect derived category as the heart of some T structure, but just complexes in degree 0. And again, you can include abelian groups in spectra. Now, when you do this, there's a unique way of completing this square. And this unique way is called the Anabelian derived functor of your original functor. So if you have a quadratic functor in sort of the ancient way, then you get a new one by deriving it in some sense. Now, when we define such functors for starting with the ones that I described before, so you take quadratic forms living on a projective module, or you take symmetric bilinear forms, or you take even forms. I'll add a little g. G stands for genuine, and this actually means that the Anabelian derived functor of the original one. And so we'll have quadratic one, symmetric one, and even one. Now, as Grisha was mentioning, we usually like to look at non-degenerate quadratic forms. And so we'll introduce non-degeneracy conditions that we will use in the constructions.
Yeah, it's interesting how you fit it in here.
Right. So there is something called, we define something called Poincare categories. And what these are is a Poincare category is a stable infinity category together with a quadratic function, satisfying some non-degeneracy conditions. First of all, you need this polar part of, so this bilinear part of the quadratic functor to be representable. So it actually needs to be maps from something to some object, which we'll call the dual of y. And if you can do this for every y, it's not hard to see that you can actually do it functorially. And so they assemble to a duality functor from the opposite of your stable infinity category to itself, and together with a natural transformation from the identity to the square of your duality. So this used to be the sort of classical setting to define these Grotnik fit groups, etc., higher Grotnik fit groups. But if you just play around with that level, you cannot avoid some too invertible assumption. So we have a sort of extension of that thing with our quadratic functor. So here's a non-degeneracy condition. So we're asking that this evaluation map is an equivalence. Sometimes it's called perfect in the literature, and that's the word we're using in our papers. And then if you have a form, meaning an object in your quadratic functor applied to a space, to an object in your stable infinity category, and you take the associated space, well, you'll say that it's a Poincare form on X if the map that you get from X to its dual by doing, how could I put it? If you have Q here, there's a natural map from Q to there, which is the projection, and we've seen that it's exactly representable by this. So we get an element here. So the map that you get that way, you want it to be an equivalence. So then you'll say that Q is a Poincare form on X. X is in your stable infinity category. And we'll also use the word Poincare object to actually mean a pair like this. So these are somehow the equivalents of in our setting of the quadratic modules that I introduced before. Right, I see that time is fleeing, so I'll try to say sort of more interesting things. So again, you can build a functor from the infinity category of Poincare categories, which is this thing. And I'm not explaining very precisely how it's constructed, but the objects are Poincare infinity categories to spectra. And you send a Poincare infinity category to the space of Poincare objects. So it is a space. So in this infinity category of Poincare categories, the one morphisms are actually exact functors of stable infinity categories together with a way of commuting with the quadratic functor, so a natural transformation. And again, they need to satisfy some non-degeneracy condition that I'm hiding here. So let's give an example of some examples of Poincare infinity categories. So assume that you already have one. Then you can construct another one called the metabolic Poincare infinity category. And its objects are arrows in C. And then you have to put a quadratic functor on the objects. And for this, when you have an arrow, you take the original quadratic functor, you apply it to the arrow, and then you take the fiber. This gives you a quadratic functor, and it's called the metabolic quadratic functor. So you see, for example, this type of construction is not hard to do with stable infinity categories. It's just impossible with triangulated ones. We then get, using this metabolic category, what we call the fundamental fiber-eco-fiber sequence in the category of Poincare categories. And what is that sequence? It's a sequence where you start, I mean, you have the metabolic category in the middle. You have the original category on the right. The map from here is just forgetting when you have an arrow, you just take the target, you forget the source. And then there's another map from C to here, where you just map L to the source L with 0 as a target. And of course, you need some kind of natural transformations. And they're, in some sense, the obvious ones. So yeah, I will not give details about this, but you have obvious natural transformations, and this gives you a sequence. And it happens to be both a fiber sequence and a co-fiber sequence in the infinity category of Poincare infinity categories. And we call this a Poincare Vertica sequence. It means a fiber co-fiber sequence in there. And then we say that a functor from Poincare categories to spectra is additive if it sends split Vertica sequences. Split is what you imagine, except that it doesn't take into account the quadratic functors. It's just the underlying sequence that is split. It sends split Vertica sequences to fiber sequences in spectra. So fiber sequences are also co-fiber sequences because spectra is stable. And so I'll give you a sort of quick definition of what higher K-theory is. Higher Hermitian K-theory, so coordinate groups. And of course, I'll cheat enormously here. So this definition says that GW is the universal additive in the above sense functor from cat P infinity, Poincare infinity categories to spectra, with a transformation from the space of Poincare forms to omega infinity of your functor. So of course, when I say this, I cheat because you need to prove that it exists. You need to construct it in some way, and that is an important part of our work. So it's constructed in our work as some kind of Hermitian Q construction. And the way we view this type of construction is something that has to do with higher cobordism categories, not cobordism in the sense of algebraic cobordism with Levin and Morel, etc., but cobordism in the sense of the classical topological cobordism categories. And it's kind of a formalization of that thing. So I cannot give details about this right now because I do not have time, but that's basically what's behind this. And again, you see that once you've constructed it, it's extremely nice that you have such a universal property in that world. An immediate corollary of that definition with quotes is that if you apply it to the previous Poincare Vertica sequence, you get a fiber sequence of spectra. And it's an extremely important one because the middle term happens to be much simpler than it looks. For this, you need to introduce the hyperbolic Poincare category that sort of contains hyperbolic objects in some sense. So you take two copies of your stable infinity category, you op one, and you define a quadratic functor on that, which is just the mapping space. As you see, it's really very similar to the hyperbolic object that we had before, and you can map the hyperbolic category to the original category to get hyperbolic objects. But you also have a sort of pair of functors that go one way and the other from the hyperbolic category to the metabolic category. And if you have a pair here, you can map it to that. And the other way around, if you have an arrow, you can map it to the pair where you put L and you put the dual of the cofiber. And it happens that if you apply GW to these arrows, well, you get inverse equivalences. So in some sense, this metabolic category that kind of depends on the quadratic functor is actually, after applying GW, gives you something that does not depend on the quadratic function. And so you can replace that middle term by GW of the hyperbolic category. But as some people will expect, GW of the hyperbolic category is actually K-theory in a sort of natural way, essentially, because if you take Poincare objects of the hyperbolic category, it's extremely easy to see that it's just actually objects of C. Now, you get out of this by replacing the middle term by K-theory, you get a fundamental sequence that we call the Botkin-Auer sequence, where you have the K-theory, GW, and the fiber is a GW of loop spaces of the quadratic functor. So you just loop it afterwards. You map to spectra and you loop. And now, in the minute that is left, somehow, I'll give you a sketch of proof of Karoubi's conjecture using all this bunch of things. So first of all, I'll reprint the sequence that we had before. And I'll recall that we are interested in this fiber. So we're doing things at the level of spectra, but then you take omega infinity and it all works out. And if you just look at what this is, well, it's just that. Now you can do the same thing, but apply to the Botkin-Auer sequence using the suspension of your quadratic functor, and you will see that V is just loops on that. In other words, V is just omega of U of sigma 2q. So you shift twice the quadratic functor and you loop the resulting spectrum. This you can call abstract Karoubi periodicity in some sense. Now, what happens for derived categories? Well, the suspension induces the following things. This is something that is very well known for people working with triangulated categories, etc. So if you suspend twice the quadratic functor, you get the anti-symmetric quadratic functor. If you suspend twice the symmetric one, you get the anti-symmetric one. And the same thing happens for the genuine ones, the Anabelian derived functors. Suspend twice, you get anti-symmetric version. So of course, this is specific to that category. It does not happen if you plug in things more complicated, like spectra. And we're going to use these, just these, not actually those for the moment. So then you need to use some comparison result that is a very beautiful result due to two of the 9 authors, Hebestreit and Steimle. So they figured out a very nice way of comparing classical K-theory or classical Hermitian K-theory to our world using T structures and hearts. I really like what they wrote. We tried to do it and they managed a lot better somehow. So I really recommend their paper. Anyway, what it tells you is that the classical Grothendieck space of quadratic functor, a classical one in some sense, is really loops of that thing, and I should add in positive degree. So this is only after taking connective covers. Compared to the, and you see here what happens is that it's the Anabelian derived functor. So it's these really. And then you just put everything together and you get the conjecture, because you look at this and you identify this thing using this in the two cases that you're interested in. And you identify it with a classical thing on both sides, and you have the results. So how am I doing in terms of timing? I think my time is basically over. Is that correct?
Well, you started a little bit late. You can at least another 5 minutes. It's certainly okay.
Okay, so then I'll take maybe 2 or 3 minutes to give a list of other features of theory somehow, just a kind of list. So first of all, something that I did not discuss is that a lot of things are actually built on the fact that we can just construct a sort of fundamental fiber square that relates Grothendieck theory to L theory. So people who know about Vig groups, that's really what this is somehow. And C2 fixed points of usual K-theory, and then Tate fixed points of usual K-theory. So this is true in full generality. There are no assumptions. And it's extremely useful for computations on this to actually go down to this, which is usually has a lot more periodicity, and this that is a lot more, that is well known in some cases. Also, something that I did not say is that we understand very well with all the quadratic functors are on the derived category, and R can actually be more than a ring. It can be a ring spectrum, and it doesn't have to be commutative. In general, somehow these quadratic functors correspond to what we call genuine invertible modules with involution. And if you were in the commutative case, it's somehow line bundles with some kind of involution. And inside you can fit the formalism of form parameters of back and rings with involutions. So this also lives in our world in a way that we understand, that I did not describe here because I do not have time, but it also is understandable. The other thing maybe that some people want to know is that there's a way of repackaging this whole theory into a C2 equivariant spectrum, real K-theory. And then it looks like this, very briefly. You have a genuine C2 spectrum. So if you do not know what this is, I cannot explain it right now. It's just for people who do. But basically, it's a sort of nice C2 enrichment of spaces with an action of C2. Oh, sorry, of spectra with an action of C2. And such a thing has an isotropy separation square, and the isotropy separation square that has the genuine fixed points, the geometric fixed points, homotopy fixed points, and the Tate fixed points is actually that square. So if you repackage it that way, that's how it looks. Right? Maybe in that world, it's interesting to see that Karoubi periodicity takes the form of a suspension somehow. You suspend by the sphere, so the smash product of the usual sphere with the representation sphere with the sign. Again, if you do not know what this is, I do not have to really have time to go into details, but some people really like C2 equivariant theory. Actually, I do. The other thing is that we have some computations of the Grothendieck bit groups of Z up to 20,000, and the reason we stop at 20,000 is because that's where the Van Diver conjecture has been proved. If you assume the Van Diver conjecture is for all i's, and this is using a lot of that because we compute these things. We have some solution to Thomason's homotopy limits problem that says that if you take two-adic completion of the symmetric Grothendieck space, and you for some small rings like number rings actually, then you get equivalence here for positive I. Oh, non-negative. So this is also using a lot of this square up there, And then we have some work in progress on schemes to work out details on schemes. I mean, it's not very difficult, but some things have to be worked out. And we also have some work in progress on representing Hermitian K-theory in the Motivic world without any assumption on two, which kind of course, should follow from our work, and up to some details follows. Right, I'll stop now.
Okay, let's all unmute and thank Baptiste for a wonderful talk. So let's have some questions. Maybe I can ask the first one. If we go back to your fiber sequence with a forgetful map and a hyperbolic map,
yes,
that reminds me of the Wood co-fiber sequence relating real and complex K-theory with the Hopf map, the first Hopf map eta. Is that a very special case of what you prove there? Or?
I'm trying to go back to the sequence, but let me think. Well, it has to be related to that, but I cannot give a precise relation right now.
I think you need a definition of your stuff for topological categories. Once you've done that, it would be pretty much automatic.
What is a topological category? I mean,
for example, you could talk about projective modules over a topological ring, and they have a topology, and you take BGL with a topological interpretation instead of BGL with a discrete interpretation. That's the difference between the K-theory of the complex numbers discrete and the K-theory of the bundles over the complex numbers, which is known as topological K-theory. That's just a sort of idea.
Yeah, so I'm not sure about that, but again, yeah, I don't know how to say something precise, but the K-theory of complex numbers again can be interpreted as, I mean, in the style of Atiyah as real K-theory, etc. And that has to be related to what we're saying, especially the C2 equivariant version. I mean, right. That's all I can say without being lengthy.
Okay, thanks. Any other questions?
Baptiste, sorry, do I clearly understand that the hardest part of the improving the conjecture of Karoubi-Giffen is to show the universal properties of infinity Poincare category, infinity categories? I mean that as soon as you establish the universal properties, then the rest is more or less modular technicalities, is straightforward.
No, it's not so clear. I mean, assuming you had the universal property, it's not so clear how to deduce, at least not to me, how to deduce that square somehow. And the fact that it's a fiber square. And you really need this to understand the rest. So in some sense, this is basically the heart of the problem, the heart of the matter. And really this comes out of different things, but among other things, a sort of concrete description of what this really is in terms of some kind of Q construction. And the other thing that I wanted to say maybe is that, sorry, I'll just play this thing again. You see, one of the reasons, sorry. There. One of the reasons that there is a lot of improvement here is that to actually prove these conjectures of Karoubi, you need to go through the derived world and to shift things, etc. There's no way you can do things by just using the original formulation somehow. you can see through this proof that really, you see, we're interpreting this using this, and then you shift this, and then you interpret that thing again. And this definitely goes through the higher world somehow, the derived world, and you cannot, I mean, I don't see at all how you can approach this through the sort of original formulation somehow.
Okay, just go ahead if you have a question. I see there's one question in the chat from Oliver Rundings. Do you see that, Baptiste?
No, I do not see that. Can you, sorry.
I can read it for you then. So
Yep.
Oliver asks the following: is the motivic representation in SH of the integers given by a motivic spectrum built out of quaternionic Grassmannians?
Well, in some sense, yes. Yes. But again, I would like to stress that all the details of that thing have not been checked, and there are still some issues in certain proofs. So I do not want to claim that everything is done.
Okay, but Grassmannians is sort of part of your construction for the representability in SH of the integers, I guess.
Right.
Thanks. Any other questions?
Yeah, really quickly, how can you compare what you did with the earlier work of Schlichting about the Karoubi conjecture?
Well, basically, so as far as I know, I mean, if we're referring to the same thing, so Schlichting has to assume things about two, and we do not.
Okay, thanks.
Okay, and there's a reply by Oliver in the chat. He says that such a spectrum appears in Arun Kumar's thesis, so it's good to know that it represents your theory. Thank you.
Right.
Okay, any final questions?
Can you say some details about the proof of theorem about metabolic and hyperbolic categories on the previous slide, or at least a principle why this theorem is should follow from the universal property definition? Any comments?
Well, I'm not saying the universal property. I'm saying so these the functors that satisfy this that they turn this thing into an equivalence, we call them Bordism invariant functors, because in our cobordism category interpretation of the Q construction, that's what they are, and then you need to prove that this is Bordism invariance, and this is related to how it relates to L theory, etc. So it's not, I mean, I'm not claiming that there's an obvious proof directly out of the universal property. I'm saying we have a construction, and that fact follows from the construction. I'm not saying either that there's no proof out of the universal property, because of course the universal property defines the thing if you believe it, but that's not how we do it.
Okay, I understand. Thank you.
Okay, I think that's all for today. Let's thank Baptiste again for his talk.